Continuing our conversation about exponents, we're going to look at exponential functions. So an exponential function is a function that can be described by an equation of the form y equals a bx. So it's a times b to the x power, where a is not equal to 0, so we don't end up with just a y equals 0. B has to be greater than 0, so again, we don't end up with a y equals 0. And b cannot be 1. So that we end up with a base of 1. That wouldn't be very exciting either. All right, so let's take a look at each of these functions. So we're going to graph each function, we're going to find the y-intercept, and we're going to state the domain and range. So here is my exponential function. Remember, a function describes a set of data where each input has only one output. So it's already described as a function for us, so we know that that's going to be the case. Each input will have only one output. So we're going to go back to basics here. The easiest way to graph these exponential functions is to make a table. There's nothing else fancier that we can do with it. So I'm going to make a table. I do want to see some negatives. I want to see 0, and I want to see positive. I want to know where the y-intercept is, so I want to see the 0 in there. But I want to see both sides of my y-axis. I'm going to throw these into a calculator, pretty straightforward here. And I come up with a table of ordered pairs that I can graph on my coordinate plane. So I'm going to graph those, and this is what we're going to start to see when we see an exponential function. It's kind of look like a water slide here. I kind of come down, and then it tapers off and gets really flat. Now you'll notice what happens here when I work with my exponential function. If you remember when we talked about our exponents, we say that we can never, if I have an exponent of 1, I end up with a base of 4. But notice what's happening here as I kind of go backwards. If we think about going backwards in this table here, you'll notice I'm dividing by 4 each time as I go. And there's no way for me to divide by 4 and ever get to 0. I can never take a number, divide it by 4, and end up with 0 as my quotient. So you'll notice what happens here at kind of the bottom of this water slide is it flattens. It looks like it's flattening out and getting closer and closer to 0, but it's never actually going to touch to 0. So it'll get closer and closer and closer, and as we try to round this number, it'll get longer and have more zeros in its after the decimal place here, but it's never actually going to get to 0. So again, when we think about those exponents, we can't really use 0 when we're talking about an exponent or a power. So this is what my graph of this particular exponential function looks like. This is called a graph of exponential growth, because we always go left to right here. I've been going backwards, but we always go left to right, because as my numbers on my x-axis increase, my y values increase hugely. They get really, really, really large. That's what our exponents do. They're very powerful. So we call this exponential growth because it's going to get bigger and bigger and bigger as we increase our x values. So to go back to these questions, find the y-intercept. The y-intercept is 1. There it is on our y-axis. Find the domain. So the domain for this, x, we could choose anything we want for x here. There really is no qualifications on what x can be. So our domain, x, is any real number that we'd like. And our range, now our output for this, we never got to 0. We never actually got below 0 either. So for this one, our range is y such that y is greater than 0. It can't actually be 0 here. But our range in this particular case is any number that's larger than 0. So here is an example of exponential growth, what this looks like. Again, increasing on our coordinate plane. All right, let's look at a couple more here. So we're going to graph y equals 1/2 x. Again, I'm going to make a table. I want to pick a few negative values. I want to choose 0 so I can see my y-intercept, and I want to pick some positive values. I'm going to chug these into my calculator. We did start with a fraction here, so I'm going to continue with a fraction as I make my table. I continued with my fractions. When I graph it, it looks like this. So you'll notice this is, again, that kind of water slide view of a graph. This one is going down, so this is actually exponential decay, because as our x values increase, our y values decrease. And again, they decrease smaller and smaller and smaller, but they never actually get to 0. So they kind of flatline there at the bottom, but they're never going to get to 0. So don't have this cross your x-axis, please. It will not cross the x-axis. To go back to answer some of our questions here, our y-intercept is 1. Our domain, and you can write it this way, or you can use our set notation that we used in the first example. Our domain is all real numbers. We can choose any kind of real number we want here. And our range are all real positive numbers. So for this one, we can use any number that's larger than 0, which happens to be all positive real numbers for that. So here's our exponential decay, what that looks like on our graph. Again, notice that our y values are continuously getting smaller and smaller and smaller, but they're never actually going to get to 0 because I'm continually dividing by 2 here. I can't divide by 2 or multiply by 1/2 and ever end up with a product of 0 for that one. All right, let's look at a word problem. A certain bacteria population doubles every 20 minutes. Beginning with 10 cells in the culture, the population can be represented by the function b equals 10, 2 to the t power, where b is the number of bacteria cells and t is the time in 20 minutes increments. This is kind of a weird one, or 20-minute increments there. How many will there be after 2 hours? So the first thing I need to do, since my t is my time, but it's in 20-minute increments, I need to break up this 2 hours into 20-minute increments. So 2 hours is 120 minutes. 120 minutes divided by 20 gives me 6 20-minute increments. So I'm going to use 6 for my t here. Now I want you to notice about this particular exponential function is that I have 10 times my t to the second power. Notice order of operations here always says do our exponents first, so parentheses and then exponents. I need to do the 2 to the 6th power first, and then I'm going to worry about the 10. So 2 to the 6th power is 64, and then I'm going to multiply that by 10. Order of operations is super important when we work with these exponential functions. We need to make sure we do the powers first, and then any multiplication afterwards. So we end up with 640, so we have 640 cells after 2 hours.